Hey guys, how's it going? Mr. Mitchell here. In this video we're going to look at Einstein's mass-energy equivalence. So let's get started. It starts by saying that when measured accurately, the sum of the masses of the particles produced by a reaction is actually slightly less than the sum of the masses of the particles before the reaction. So that means there's a very small amount of mass lost in a reaction. And it says that this lost mass is turned into energy according to Einstein's mass-energy equivalence principle, E equals mc squared. And this is the famous equation from Einstein that you might already have heard about, where E is the energy released in the reaction measured in joules, m is the lost mass or mass loss measured in kilograms, and c is the speed of light in a vacuum measured in meters per second. So remember that takes a value of 3 times 10 to the 8 meters per second in a vacuum. And it says to note that through this principle, mass can be turned into energy, but energy can also be turned into mass. And that's why it's called the mass-energy equivalence, because Einstein said that if you get mass, it can be turned into energy, and if you get energy, it can also be turned back into mass. And I'm just going to show you a quick simulation to help you visualize how this was discovered. So if you look down here, it tells us that experimental evidence for the conversion of mass to energy is found when a neutral pion decays into gamma radiation. If the neutral pion has no kinetic energy before the decay, the total energy of the gamma radiation emitted is found to be equal to the mass of the neutral pion times c squared exactly, i.e. mc squared from E equals mc squared. So we've got our neutral pion here, and if I click play, you'll see it decays into 2 gamma rays going in different directions there. And it says that 2 gamma rays are produced, which conserves momentum. So this shows us the evidence that mass can be converted into energy. Jumping back to the notes now, it says the energy released by reaction can be calculated by finding the difference in mass between each side of a nuclear equation. So this is a very common exam style question where you're asked to calculate the energy released in a reaction. And there's a certain structure to how you want to answer this kind of question. And we'll do that in the worked example video for Einstein's mass-energy equivalence. So check that out so that you get plenty of practice of doing these kind of questions. I've also given you some top tips here for when you're doing these calculations. So the first top tip is do not round off any numbers mid-calculation, as small quantities of mass are important here. So you might be dealing with masses that have about 3 or 4 decimal places, and what I'm saying here is that you want to keep those numbers of decimal places until the very end of your reaction, when you can then maybe round your total energy calculated, but before that you want to keep every single digit that you have. And lastly, top tip 2 isn't really necessary, but it says rather than having to square the speed of light in your calculator every time you do these calculations, it's quicker to use the value for 3 times 10 to the 8 squared, which is 9 times 10 to the 16. So that's the same as squaring the number here 3 to get 9, and just multiplying the power here by 2, because we've got 8 times 2 there, which gives us 16. So what's involved in these kind of calculations? Well, typically you're wanting to use this equation here, E equals mc squared, to find the energy lost in a reaction. However, before you can do this, you need to know what the lost mass is in a reaction. So what you might be given is a nuclear reaction, such as this one that we looked at for the alpha decay, where you've got uranium-238 decaying into thorium-234 plus an alpha particle. And you might be given the masses of each of these, and you can then use those to find the lost mass. So how would you do that? Well, you would basically just take your total mass before the reaction, which would just be the mass of the uranium nucleus, and then your total mass after the reaction, which would be the mass of this nucleus plus the mass of the alpha particle. And if you add those together, you would get your total mass after the reaction. And then remember we said that the total mass before is going to be slightly larger than the total mass after to give us that slight loss in mass. So that means you would then take your total mass before the reaction and subtract your total mass after the reaction to get your lost mass. That then gives you your m value in this equation, and then you can multiply that by the speed of light squared to get the energy released in the reaction. And this kind of question is a common one to be asked in the exam, so I'd make sure you can do them. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video a thumbs up, subscribe to the channel, and I'll see you in the next one. Take care.